So how do we measure the distances to stars? Uh, it's not trivially easy. You can't just look at a star and say, oh, well, yes, that one's obviously 5 light years away, and that one's 100 light years away. When we look at the stars, especially with the naked eye, all the stars just look like they're up there on the celestial sphere, right, hovering above the Earth's surface. So how do we figure out the depth in the universe and how far away these stars are and which stars are close and which stars are far? How do we figure this out? The first method that was devised, and the simplest method, is using what's called parallax. Parallax is the phenomenon where objects appear to move across your field of view, not because the objects are moving, but because you're moving. And as you look at the world through different points of view, objects look like they've moved relative to you and relative to each other. This is true in everyday life, and it's also true in astronomy, right? Let's say the Earth starts out here on some day of the year, and then some nearby star in the galaxy, it's going to appear from Earth's point of view like it lines up in front of this star. And then as the Earth moves around the sun month after month after month, that star is going to look like it's moving relative to the background stars, such that 6 months later, now this red star in the foreground is actually going to look like it lines up in front of this star. So that over the course of 6 months, as the Earth moves through space, this red star is going to look like it wobbled over to the left. And then over the next 6 months, as the Earth finishes its orbit around the sun, that red star is going to look like it wobbles back over to the right. Right? The star isn't moving, the sun isn't moving, it's the Earth that's moving. And so those of us standing on the Earth looking at this red nearby star will see that the red star looks like it has shifted over to the left over 6 months and then shifted back over to the right over 6 months. How does this help us get distance? Well, if you look at the diagram of the Earth, the sun, and this star like this, then you'll notice that what we have is a right triangle. And if you remember a little bit of trigonometry, once you know you have a right triangle, well, then your job has become immensely easy. This is one of the reasons why geometry and trigonometry were invented, is to do things like say, well, if I have a right triangle, can I figure out the length of this side of the triangle? Because if I have the length of this side, I now know the distance from our solar system out to that star. And if you remember your trigonometry, you know that if you know the length of one side of the triangle, and if you know one angle, you can basically figure out everything else using sines, cosines, and tangents. Well, we know what this side of the triangle is. This is just the distance from the Earth to the Sun, so this is 1 astronomical unit. So if we have this side and this angle, which I'll call P, we can figure out distance. Well, how can we measure this side of the triangle? Well, if we keep this line going up to infinity, out to the stars, then this angle is the same as this angle. So all we need to do is watch that nearby star, watch it wobble over to the left over 6 months, wobble back over to the right over the next 6 months, take this full angle that the star appears to have wobbled by. Half of that is our angle P. This is why we symbolize it P for parallax. Right? The parallax angle that we see is not the full wobble of the star. We're only taking half of that because this is the half that we need to solve for the triangle and get the distance. How are parallax angle and distance related? Well, let's imagine that this red star was closer. Okay, I'm going to sort of tweak my graphic here and say, well, if this red star were closer, notice that the parallax angle is now wider, right? That star is going to wobble through a greater angle over the year, not because the Earth and the Sun have changed. The Earth is still 1 AU away from the Sun, but just because this length is shorter makes this whole triangle is now shorter and fatter, so that the parallax angle is wider. So you see a larger parallax angle for nearby stars. If I stretch this graphic, then you'll notice that when the star is farther away, we've now created this long, skinny right triangle such that the parallax angle is smaller. This is how we can figure out the distances to these stars. All we've got to do is measure this parallax angle, and the greater the parallax angle, the closer the star must be. The skinnier, the smaller the parallax shift in the star, the farther away the star must be. So all we need to do is watch the stars, watch the sky month after month after month for a year, measure the shift in these stars, get that parallax angle, boom, we've got the distance. It's a fairly simple and elegant method for seeing, for calculating, for determining the distance to the stars. Unfortunately, it's not that easy, because if it were that easy, people would have been doing it thousands of years ago. The thing that ancient astronomers couldn't conceive of is that the distances to the stars are very, very, very far away. And since these distances are trillions of kilometers, these parallax angles, kind of like this graphic here, right? The greater the distance, the smaller the parallax shift. The fact of the matter is, stars are so far away that that parallax angle is so tiny you can't see it with the naked eye. Right? Remember, every optical device, every telescope, every pair of binoculars, and your eyes have a resolution limit. Right? There is a resolution beyond which, or there are details on the sky too small for your eyes to be able to resolve. And our naked eyes can't see the parallax shift of stars. To our eyes, this angle, to our eyes, this wobble is so tiny that the stars just look like they're standing still. So you need telescopes, right? The fact of the matter is, these angles, the parallax angles of stars, are so tiny we measure them in arc seconds. Right? What is an arc second? Right? 1 arc second, which is the two ticks, right? 2 quotation marks is arc seconds. 60 arc seconds make up 1 arc minute, and then 60 arc minutes make up 1 degree, and then 360 degrees makes 1 great circle around the sky. So we measure these parallax angles in arc seconds. That's how small these little shifts are in the stars. You can't see that with your eye, but you can see it in a telescope, if your telescope has a small enough resolution angle. If you can see the parallax shift in the star, you can figure out the distance. And how are we measuring this distance? Well, much like we've been doing so far in the class, we're going to make up a unit of measurement to make our lives easier, to make the math easier. So we invent this unit of distance called a parsec, such that 1 parsec is the distance that a star must be for its parallax angle to be 1 arcsecond. So if a star has a parallax angle of 1 arcsecond, that star, by definition, right, we've just made up this unit to say, if a star has a parallax angle of 1 arcsecond, how far away is it? It's 1 parsec. Though that's the rules of the game that we just made up. Again, because when you've got the rules of trigonometry to help you solve these problems, it turns out that the relationship between distance and parallax angle is very simple. The distance to a star in parsecs is just 1 divided by the parallax angle in arcseconds. You always put in the parallax angle in arcseconds, and the distance comes out in parsecs. The math is nice, the equation is simple. Why? Because we made up this unit of parsecs in order to, intentionally, we made up this unit of parsecs intentionally and specifically to make the relationship simple. Right? So one of the first stars, one of the first astronomers to be able to measure parallax angles was a German by the name of Friedrich Bessel. in the 1800s, and one of the first stars that he was able to measure the parallax angle for was this star 61 Cygni. So the name of the star is 61 Cygni, and he watches this star and sees that it has a parallax angle of 0.3 arc seconds. Well, distance is just 1 divided by the parallax angle. So if this star has a parallax angle of 0.3 arc seconds, 1 divided by 0.3 is 3.3. So that star must be 3.3 parsecs away. All right, I probably haven't answered the question that's top of your mind, which is, all right, so that star is 3.3 parsecs away. What the heck does that mean? What the heck is a parsec? Well, once you make up this unit, the parsec, it turns out that 1 parsec is equal to over 200,000 astronomical units, or 1 parsec is equal to about 3 light years, so 3.26 light years. So we make up this unit, the parsec, and we say, great, that star is a parsec away. Well, how far is a parsec? Well, a parsec is 3.26 light years. So if you wanted to know, like some of the questions in the homework ask you, if you want to know the distance to a star in light years, you would take 3.26 divided by the parallax in arc seconds, right? Because 1 divided by the parallax in arc seconds gives you the distance in parsecs. Then you multiply by 3.26 light years per parsec, and that tells you the distance in light years. The parsec is essentially the last unit that we're going to make up to measure the distances to objects in the universe. After you've invented this parsec, now you can just start using these metric prefixes, right? If something is thousands of parsecs away, you could talk about the distance in parsecs, or you could say kiloparsecs, right? Where a kiloparsec is 1,000 parsecs. For really far away objects like other galaxies, you might measure the distance in megaparsecs, where a megaparsec is 1,000,000 parsecs. But beyond that, now you've got those metric prefixes, kilo, mega, giga, to simplify things. We don't need to make up another unit of distance after this. Isn't that a relief? So the parallax method for figuring out the distances to stars is nice and elegant. All you got to do is measure the parallax angle. Distance is 1 divided by p. You've got the distance, if you can see the parallax angle. Now remember, as stars get farther and farther away, their parallax angle gets smaller and smaller and smaller. Well, at some point, that parallax angle is going to get so small you can't resolve it anymore. And the star just looks like it's standing still. And if you can't measure the parallax angle, you can't use this method to get the distance. Where does this fail? Where does this method fail? Well, the new gold standard for getting parallax distances is with this instrument called the Gaia spacecraft that launched a few years ago. And the Gaia spacecraft has been running for the last several years, watching the whole sky, seeing as many stars as it can see, and getting as many parallax measurements in it as it can. And the Gaia spacecraft is magnificent. Like, I don't want to undersell this. The Gaia spacecraft is fantastic because Gaia can measure parallax angles as small as 1/10,000th of an arc second. How far away is that? Well, if there's a star with a parallax of 1/10,000th of an arc second, that star is going to be how far away? Well, distance is 1 divided by parallax. So then what kind of a distance is that? Well, the distance is 1 divided by 0.001 arc seconds. That comes out to 10,000 parsecs, or 10 kiloparsecs if you want to. This is an artist's sort of drawing, or an artist's representation of our galaxy. Here's the sun. 10,000 parsecs is out to here. So we've been able, now our galaxy is huge. The whole galaxy is about 30,000 parsecs in diameter, or about 100,000 light years. 10,000 parsecs is a giant slab of space. And it's not the entire galaxy, mind you. But the Gaia mission has been able to observe, measure the parallax, and calculate the distance to a significant fraction of the galaxy. The Gaia catalog, when I say it's magnificent, what do I mean? I mean the Gaia catalog has measured the parallaxes and the distances to over 1 billion stars. Billion with a B. So now, for pretty much all of the stars, or maybe not all of them, but for most of the stars in that yellow circle, if you want to know how far away that star is, all you got to do is go on the website, type in the coordinates for that star, and the Gaia catalog will spit out the parallax and the distance. It is a massive tool for figuring out properties of these stars. It's absolutely awe-inspiring. But it's not the whole galaxy. If you want to know the distance to a star out here or out here, if you want to know the distance to a star on the far side of the galaxy, those stars are too far away. Their parallax angle is too small to see. The stars just look like they're standing still. So how do we figure out the distances to those stars? We've got to come up with another method, right? The parallax method works great out to here, this far away. Once you start talking about faraway stars on the other side of the galaxy, or if you want to talk about the distances to other galaxies, you've got to invent a new method that does work at those greater distances. Parallax won't work, but we figured out other ways to get the distances to those stars and those other galaxies. But that's a story for another day.